Logarithmic functions. A population of 50 flies is expected to double every week, leading to a function of the form f of x equals 50 multiplied by 2 to the x power, where x represents the number of weeks that have passed. When will this population reach 500? Trying to solve this problem leads to 500 equals 50 multiplied by 2 to the x power, dividing both sides by 50 to isolate the exponential, 10 equals 2 to the x power. While we have set up exponential models and used them to make predictions, you may have noticed that solving exponential equations has not yet been mentioned. The reason is simple. None of the algebraic tools discussed so far are sufficient to solve exponential equations. Consider the equation 2 to the x power equals 10 above. We know that 2 cubed equals 8 and 2 to the 4th power equals 16. So it is clear that x must be some value between 3 and 4 since g of x equals 2 to the x power is increasing. We could use technology to create a table of values or graph to better estimate the solution. From the graph, we could better estimate the solution to be around 3.3. This result is still fairly unsatisfactory, and since the exponential function is 1-to-1, it would be great to have an inverse function. None of the functions we have already discussed would serve as an inverse function, and so we must introduce a new function named log as the inverse of an exponential function. Since exponential functions have different bases, we will define corresponding logarithms of different bases as well. Logarithm. The logarithm base b function, written log base b of x, is the inverse of the exponential function, base b to the x power. Since the logarithm and exponential are inverses, it follows that properties of logs, inverse properties. Log base b of b to the x power equals x. B to the log base b of x power equals x. Recall from the definition of an inverse function that if f of a equals c, then f inverse of c equals a. Applying this to the exponential and logarithmic functions, we can convert between a logarithmic equation and its equivalent exponential. Logarithm equivalent to an exponential. The statement b to the a power equals c is equivalent to the statement log base b of c equals a. Alternatively, we could show this by starting with the exponential function c equals b to the a power, then taking the log base b of both sides, giving log base b of c equals log base b of b to the a power. Using the inverse property of logs, we see that log base b of c equals a. Since log is a function, it is most correctly written as log base b of c, using parentheses to denote function evaluation, just as we would with f of c. However, when the input is a single variable or number, it is common to see the parentheses dropped and the expression written as log base b of c. Example 1. Write these exponential equations as logarithmic equations. Example 2. Write these logarithmic equations as exponential equations. By establishing the relationship between exponential and logarithmic functions, we can now solve basic logarithmic and exponential equations by rewriting. Example 3. Solve log base 4 of x equals 2 for x. By rewriting this expression as an exponential, 4 squared equals x, so x equals 16. Example 4. Solve 2 to the x power equals 10 for x. By rewriting this expression as a logarithm, we get x equals log base 2 of 10. While this does define a solution and an exact solution at that, you may find it somewhat unsatisfying since it is difficult to compare this expression to the decimal estimate we made earlier. Also, giving an exact expression for a solution is not always useful. Often, we really need a decimal approximation to the solution. Luckily, this is a task calculators and computers are quite adept at. Unluckily for us, most calculators and computers will only evaluate logarithms of 2 bases. Happily, this ends up not being a problem, as we'll see briefly. Common and natural logarithms. The common log is the logarithm with base 10 and is typically written log of x. The natural log is the logarithm with base e and is typically written natural log of x. Example 5. Evaluate log of 1000 using the definition of the common log. To evaluate log of 1000, we can let x equals log of 1000, then rewrite into exponential form using the common log base of 10, 10 to the x power equals 1000. From this, we might recognize that 1000 is the cube of 10, so x equals 3. We also can use the inverse property of logs to write log base 10 of 10 cubed equals 3. Example 6. Evaluate the natural log of the square root of e. We can rewrite natural log of square root e as natural log of e to the 1/2 power. Since natural log is log base e, we can use the inverse property for logs. Natural log of e to the 1/2 power equals log base e of e to the 1/2 power equals half. Example 7. Evaluate log of 500 using your calculator or computer. Using a computer, we can evaluate log of 500 approximately 2.69897. To utilize the common or natural logarithm functions to evaluate expressions like log base 2 of 10, we need to establish some additional properties. Properties of logs. Exponent property. Log base b of a to the r power equals r multiplied by log base b to the a. Properties of logs. Exponent property. Log base b of a to the r power equals r multiplied by log base b of a. To show why this is true, we offer a proof. Since the logarithmic and exponential functions are inverses, b to the log base b of a equals a. Raising both sides to the r power, we get a raised to the r power equals b raised to log base b of a raised to the r power. Utilizing the exponential rule that states x raised to p to the q power equals x to the pq power, a raised to r equals b raised to the log base b of a raised to the r power equals b raised to the r multiplied by log base b of a. Taking the log of both sides, log base b of a raised to the r power equals log base b of b raised to the r multiplied by log base b of a. Utilizing the inverse property on the right side yields the result. Log base b of a raised to the r equals r multiplied by log base b of a. Example 8. Rewrite log base 3 of 25 using the exponent property for logs. Since 25 equals 5 squared, log base 3 of 25 equals log base 3 of 5 squared equals 2 multiplied by log base 3 of 5. Example 9. Rewrite 4 multiplied by the natural log of x using the exponent property for logs. Using the property in reverse, 4 multiplied by natural log of x equals natural log of x to the 4th power. The exponent property allows us to find a method for changing the base of a logarithmic expression.